Let's talk about the gradient descent. By using gradient descent, we can create an interesting art like this. Given an input geometry, we distill some information from the geometry and use the data, for example, the curveness, to drive this contour line by using the gradient descent algorithm. One of the classic example of gradient descent would be the terrain. So let's look at a terrain. This is a terrain, and we can use gradient descent to kind of map out the river curve like this, or we can draw the contour line like this. So let me explain what is a gradient. Let's look at a terrain. Alright, let's see this terrain. First, I'm going to define a function f. It's from the R3 to R. And given an input will be the position of this terrain. For example, this point would be the x, y, z. And the output value, I'm going to define it as the height of the terrain. So it will simply be y. So we put this into our function, we will simply get y, the height. And by calculating the gradient of it, the gradient, the triangle f, will simply output another new function from R3 to R3. And it will output a vector which tells us in which direction we go. Locally, it will increase our function output value. For example, we put our xyz into the gradient, and the calculate will be this direction. So basically, it tells us that when we move along this direction, locally, we can increase our function output value. That is basically climbing up the mountain. So when I put inside the position of this point into the calculate its gradient, basically it will output this direction. So what we are going to do is basically repetitively iterate putting using this gradient. So we put the function, calculate the gradient, and then we move along this direction and get this position. And then we sample the gradient again. We will get another new direction vector, and then we just move along that direction. So by repetitively doing this, we are basically climbing up the mountains. We are doing the gradient ascending. And if we don't go to the inverse direction, we are descending. So yeah, that's the gradient ascending and the gradient descending. So let's get back to Houdini. And let's see what we are doing here. First, we'll put a grid. And I use mountain to create some kind of a terrain shape. And then what I'm going to do is to define the function. The input will be xyz, the position, and the output will simply be the cost. I named the output as cost, and the function value will be the height of the mountain. And then we use measure slope to calculate the gradient of our function. So we can visualize it. Let's visualize it. You can see that for each point, we are basically getting a vector telling us in which direction we go, we could increase our height value. And because we wanted to traveling along the direction, so I might wanted to use the attribute blur to smooth the gradient calculated. And then what we do is simply, as I just stated, that I will scatter some points along the terrain and move this terrain by repetitively sampling the gradient. So we're repetitively sampling the gradient. Basically, we are using a for loop, and then we just step forward and making a polyline. And then we can visualize the result. Yeah. So that's basically it. And another interesting way to do is the contour line. Instead of climbing up along the gradient, we change the gradient as the cross product with the gradient with the normal vector. So basically we are traveling along the same height. We are not climbing up, we are instead walking perpendicular to the gradient. So it will give us the contour line. And let's see another example. The pig head. What about the general input geometry? This is not a terrain, but a pig head. So we can't use the height of this pig head as the function output value. So what can we use? Actually, we could use the curveness. Let's see the curveness. I used the measure sum to calculate the curveness at each point. And we can see the curveness. We could use this as kind of the function output value and then move along the curveness. So basically what we are doing here is, let me illustrate it a little bit. So basically what we are doing here is that I'm defining a function R3 to R, and the R3 input will still be the position of the geometry, so it is XYZ, the Euclidean coordinates, but this time the output R is not the height, is not Y, but the curveness. So we output the curveness at this point. So when we calculate the gradient will be the direction will be, well, when we move along the gradient, we are simply in the curveness will be higher. So we are simply moving along the direction of the curveness. So this time we calculate the curvature and set it as the output value cost, and the rest of the calculation will still be the same, and we can get this kind of effect. Yeah, like this. So we can see that let's see the curveness again. Let's see the curveness. And the blue is the lower value, the red is the higher value. So at this point, the gradient will pointing toward this direction. So we see when we're tracing out the curve, basically we are climbing along the curveness. So given 3D geometry, basically we could use all kinds of different information to do the gradient descent, as long as we have defined our function properly. Like in this example, we are using the curveness, but we could also use other attributes, or we could use a noise too. For example, this input geometry. I use the point VOP, and let's use a noise. So let's create a whirly noise, and we wire in the position, and let's subtract the distance 2 from the distance 1 and output it as the CD. So in this example, I'm also going to bind export this value and call it the cost. So in this example, what I wanted to do is to define a function. Let's see. In this example, what I wanted to do is to define again a function from R3 to R. For this time, the output value will be the noise value. So basically, we are moving to the gradient will be pointing to the direction to increase the noise value. So it will be look like this, from the black to the white. So from the black to the white. Let's see the result. Let's wire in the calculation and see the result. Yeah. You can see that we are basically moving toward from the black part to the white part. Yeah, so basically, as long as we have defined our function properly, we can calculate its gradient and then do any kind of magic we want. But if we just use a random noise like this, we kind of lose the relationship with the original geometry. So I would suggest to use the curveness, and it will get a better result. We could also flip the gradient and do cross product with the normal, so we get contour line like this. Finally, let's see this example. This is the contour line, and basically we are using the curveness and to drive the gradient.